In this problem, we are given the graph of the original function f of x, and then based on this graph, we need to draw an accurate sketch of its derivative. Notice, in addition, we are asked to mark clearly the places where the graph of the derivative crosses the horizontal axis. Now we can translate this. When the graph of the derivative crosses the horizontal axis, that actually tells us the value that the derivative attains at that point. By marking where the derivative crosses the horizontal axis, we're really being asked to mark where the derivative equals 0. Before we just start sketching over here, we really want to carefully understand what's happening to the original function f of x, and then based on that understanding, we'll be able to quickly sketch the graph of the derivative. So I just outlined a few key features that we'd like to pay attention to. In red, we're going to shade the parts of the graph where the original function f of x has negative slope, because we know that corresponds to when the derivative is negative valued, or below the x-axis. In purple, we're going to sketch over the portions of the graph of f of x that have positive slope. That would correspond to where the derivative has positive values, i.e. above the x-axis. Wherever the graph of the original has 0 slope, we're going to mark those points with a yellow dot. That would correspond to when the derivative graph crosses the horizontal axis. And any points where the graph of the original function has undefined slope, we're going to mark with green, and we know that's going to be points where the derivative function actually does not exist or take on a value. Let's begin by marking places where the graph of f of x has negative slope. So we'd be looking what parts of this original function correspond to decreasing. Take a moment to look at this and think, what sections would you shade in red? We would find that the original function has negative slope from negative infinity all the way till it approaches -1. Now at -1, since this is a corner, it actually has the derivative is undefined here. Okay, and then the original starts to decrease again, starting at 0, going to about 1.5, and then from about 3 to 4. And as we're noting this, one thing we'd want to pay attention to is not only the fact that all of these have negative slopes, but there's also the size of how negative they are. Notice here, we might make a note that as x goes to negative infinity, the derivative, since it's always decreasing while it's always negative, it's getting flatter and flatter, like the slopes of the tangent line as we go out are getting closer to 0. So we might note that it's getting closer to 0. That'll help us as we draw an asymptote of the derivative graph over here. Next, let's look at where the graph of f of x has positive slope. Take a few seconds to think what sections of the graph you would shade, in this case purple. We see that the original function is increasing from -1 to 0, increasing again from about 1.5 to 3, and then increasing from 4 out to infinity. And a few key notes that we want to make here. Since it's increasing as a straight line after 4, not only is this slope positive, but it's constant. So we might say that f prime of x is a constant positive value. For all x values greater than 4. So in terms of how that would look on the graph over here is at some point we would just have a horizontal line continuing out forever and ever at some positive height. Here we see that if we are looking at -1, from -1 to 0, the slopes are always positive, but at the beginning they're a much higher positive value, and then they start to level out to 0. So we'd probably have something that's starting really high and then bringing down to 0. Similarly here, they start very close to 0 and positive, increase steeply, and then start to slow down again. So maybe we'd see something like this. Okay. Next, think about where the graph of the original has 0 slope. We'll mark those points in yellow. So at x equals 0, x equals 1.5, and x equals 3, we see that we've got a horizontal tangent line to the graph of the original. So all these are places where the derivative is equal to 0 or will be on the x-axis. Now let's think about where the graph has undefined slope. And we see that the derivative is undefined at x equals -1 and x equals 4, because here we have a cusp right at -1, and here we have a sharp corner at 4. Now that we've taken time to really understand this graph very clearly in terms of its slopes, we're ready to translate all this into the graph of the derivative. Let's first mark the places where the derivative equals 0. So the derivative equals 0 at 0, 1.5, and 3. Next, let's look at what we would do for values greater than 4. From what we looked at earlier, since the graph of the original after 4 is a straight line with positive slope, we know that would correspond to a constant value of the derivative that's positive, so we just mark that here. So from 4 everywhere else, it's there. And notice I did the open circle because we know at 4, actually the derivative does not exist. Now let's look at what's happening from 3 to 4. From 3 to 4, we see that that was part of where the function had negative slope, so it should be negative. And we know that it's getting much more steeply negative, so it should be going down for a bit, and then we would have an open circle because it does have an undefined derivative at 4. So we might graph something like. Next, from 2 to 3, we see that at 2 it's 0, and then the slopes become positive, but eventually the slopes slow down. So while they're positive, at first they were increasing higher, and then the slope started decreasing, or the difference in the slope started decreasing. So we would get something like. Next, we turn our attention from 0 to 1. From 0 to 1, at first the slopes are 0, and then they are always negative, but we see that they're rather steeply negative till about this point, at which point they start getting less steep, so they start leveling out again towards 0, which would give us. From -1 to 0, we see that the original function is always increasing, so all of these will be positive values of the derivative. And specifically, very close to -1, we see a very steep slope, which would mean it would have positive values that are higher in the y-axis. And then over time, the slopes start to level out. So eventually we'd be getting slopes that, while positive, are getting closer and closer to 0. So that could give us something like. And again, since our derivative does not exist, since we have this cusp where the slopes change from being negative to in a moment then being positive, we would leave an open circle about -1. So then from -1 out to -infinity, we do pay attention to this idea that as we're getting closer to -infinity, the derivative, while always negative, should be getting closer to 0. So the graph of the derivative will have a horizontal asymptote approaching 0. And then as we get closer to -1, we get much more steeply negative. So we would show something like. So this would be just a quick sketch of the graph f prime of x.